Video in mathematics in the modern world. And today we're going to talk about problem solving using inductive and deductive reasoning. So let's have this or um, take this as an example first. We're going to follow some steps. And these steps will give us or tells us to have this. So first we're going to pick a number. And then with that number at hand, what we're going to do is to multiply that number by 10. After that, we're going to add 8 to whatever that product is from step 2. Then we're going to divide the sum from step 3 by 2. And then we subtract 4. And we're going to consider two different methods in answering this algorithm here. And anyways, an algorithm is a series of steps that we need to follow. So we usually hear those things in the internet these days. When you click on something, and the algorithm will show you some ads, and actually um Google does that, Facebook does that, about the algorithm. So this is a very fairly simple algorithm. You pick a number and then you do this stuff. What we're doing here in the internet is if you're going to click on some ads and then the internet or the website knows that you click on that ad, then it will run the algorithm. So that is a bunch of steps still. So what we're going to do is we're going to have these two processes, and let's going to split the screen over here, and we're going to consider these processes. So in process A, let's call this process A, we're going to get individual numbers. So for instance, we're going to get the number 1, 2, and 3 here. So for number 1, what we're going to do for after number 1, I'm going to pick a number. Then we multiply that number by 10. So 1 times 10 is clearly, well, 10. 10, add 8 to that, what we have is 18. Then we divide the sum by 2, that's going to give us 9. And we subtract 4 by that, that gives us 5. So pretty much we end up with 5. Now, how about for 2? Start with 2. That's a 2. Okay. Multiply that by 10. That's going to give us 20. 20, add 8 to that. It's going to give us 28. Divide that by 2. That's going to give us what? 1, 4, 14. And then subtract 4 by that. So what we have is 10. So we end up with 10. So let's consider the last digit. Let's have 3. 3 times 10 is going to give us 30. Add 8 to that. That's going to give us 38. Divide the sum by 2. That's going to give us what? 19, right? 19 minus 4 is going to give us 15. So what we can see here is we can see a pattern. We started with these numbers here on the top part. So we have 1, 2, 3. It ends up with 5, 10, and 15. So we can somehow say or guess, the proper term there is conjecture. We're going to talk about that in a while. Is get any number n. Let's call this number n, or x if you want, and we want to multiply that number by 5, and then we end up, what is the last part in the algorithm, or we end up with the solution of the algorithm. So we call it process A. For process B, what we're going to do is we're going to let a certain number, a general number, any number actually, let's say we're going to call it x, and then we're going to follow the steps in the algorithm for x. Okay, not for individual numbers, but for x. So multiply x by 10, that's going to give us 10x. Okay, and then we're going to add 8 to that product. So adding 8 means that we're going to have 10x plus 8 over here. I mean, we cannot put the 8 here in the coefficient because that will be multiplying. So this is a term separate from this. Because they're not like terms, so we cannot put 8 as a coefficient. And then we divide the sum by 2. So that's going to give us 10x plus 8 all over 2. And then we subtract 4 by that. Maybe we can simplify this first. This becomes 10x. That's a 10. 10x over 2 plus 8 over 2. If we're going to simplify that, that's going to give us what? This becomes 5x plus 4. Okay, 5x plus 4. and then we're going to deduct 4 by that. So 5x plus 4 is minus 4 is pretty much going to end up with 5x. So this is our process B, and it's very actually it's the same, taking note of the variables. So it's 5n and 5x. So what we have here in process B is we take this certain general variable x, and then what we are doing is actually by following the algorithm, what we end up with is a number, okay, times 5 of that original number. Similarly, we have here. Okay, so let's try to digest the processes here. Let's start with process A. So process A, as you have observed, use examples where a pattern was noticed between the original numbers used and the corresponding results after applying the procedure. This process is utilizing what we call inductive reasoning. Okay, so this is basically what we call a bottom to top approach. Bottom to top. So we start at the bottom with the specific examples, with the specifics, the examples at hand, and we go to the top where we generalize the procedure being done. So recall here, we start with the bottom examples, the bottom part we can imagine that in a pyramid. Um, the bottom part are the examples, the top part are the generalizations. So these are the generalizations. These are the bottom parts, which are the specifics. Okay, so this is bottom to top approach. Okay. Um, Furthermore, in inductive reasoning, the conclusion, okay, drawn from the specific examples is what we call a conjecture. Okay, so it is noted that though that a conjecture is an idea, it may or may not be correct. Specifically in mathematics, when you say the word conjecture, it means that it's an open problem. It's awaiting to be solved. It's a hunch. Okay? You provide a proof to a conjecture and you will create or you will make a theorem out of it. Okay? So there's a lot of open problems in mathematics. It's a conjecture statement which is, put on the table, then maybe anyone can answer that if you cannot. So what we did here in this algorithm, this is what we call a conjecture. So we only tried to observe the pattern from 1 to 3. How about for 4, 5, 6? Will this still hold? Or is there any number along the number line that this conjecture is not following? So that's why it's called a conjecture, because we're not sure if it's true for everything. Next, we're going to consider the process B. The second process took the generalization first of the procedure and expressed it algebraically. So we did some algebra there, from which, applying the rules of algebra, the principles, the axioms, it was simplified to where the number is picked. This led us to conclude that doing the process leads us to a number 5 times larger than the original number picked. As we can see, we ended up with 5x. So the process um, in this one, okay, the process in this one is what we call deductive reasoning. We start with generalization and end up with we can plug in examples right after. So in deductive reasoning, the conclusion drawn from applying generalizations, procedures, or principles, okay, um, this is also known as the top to bottom approach. So again, the conclusion is drawn from generalizations, okay, from the general concept. So this is top to bottom approach. Going back in the example, this is top. We start with the specific example, and then or we start with the generalization, the formula itself, and then we can end up with the specifics. I mean, you can just substitute the values here for x, for any x you want, since you know that applying the algorithm will end up with this formula. So why would you follow the algorithm if there's a shortcut formula for that? So that's deductive reasoning. And let's talk about more about them. So inductive reasoning, what is it? So the type of reasoning that forms a conclusion based on examination of specific examples. That's inductive reasoning. The conclusion formed by using inductive reasoning is what we call a conjecture. So since it may or may not be correct. Again, a conjecture is an open problem. It is waiting to be solved. And let's talk about counterexamples. A statement is a true statement if it is true in all cases. Similarly, in a conjecture, in order for it to be true in all cases, you must provide a proof. If you can find one case for which a statement is not true, which is with what we call a counterexample, then the statement is what we call a
It's
false
12
statement. Okay,
o'clock.
even though you thought that it's correct at first. Okay, so that's a counterexample. Let's start with deductive reasoning. Talk about that. This is another type of reasoning. In this lecture. Deductive reasoning is distinguished from inductive reasoning in that it is the process of reaching a conclusion by applying general principles or procedures. Okay, just like we did it algebraically. So we didn't start with the specifics. We started with the formula. So in a nutshell, what is deduction versus induction? Okay, let's start with deduction. So deduction starts with a theory in mind. After you see the theory, you will try to hypothesize. Okay, and then have some observation, and then you confirm that the theory indeed is correct. So that's what we call deduction. Okay, and then one of the people who use that, popular people, is Aristotle. And induction starts with the observation. Actually, after the observation, you somehow see a pattern out of it, and then you hypothesize that, hey, maybe this is true, and then therefore you will produce a theory out of that. And one of the popular figures that use induction is, Sherlock Holmes. He finds some observations first. He makes a pattern, and then he hypothesizes, and then he makes sure that it's correct, um, about his examination about that observation. So that is induction versus deduction. So how do mathematicians think, by the way? So actually, it all starts with induction. So a mathematician observes first that, hey, this is interesting. He observes a pattern out of that. Then you hypothesize that pattern. You create a draft, a conjecture, and then you prove that, making it a theory, a theorem actually. Okay, and then you try to prove that. Okay, how do you prove that? You prove that using the deduction procedure. You have the theory, you have the hypothesis, you hypothesize that, and then you observe, and then you confirm that indeed the theory is correct. Okay, so that's induction versus deduction. So for instance, let's try to answer these. Predict the next two numbers in the sequence. So here for number one, we have 3, 6, 9, 12, 15. It's trivial to know or to check that it's 18 and 21. Why is it 18 and 21? Because they're all multiples of 3. So 3, 6, 9, 12, 15, and then we add 3, 18. We add 3, it becomes 21. Number two, maybe you can answer this. 1, 3, 6, 10, 15. Two blanks. You can pause the video. Okay, so what's the answer? The answer should be after 15. Um, so we try to think of this. So we try to get the difference. Actually, how we get the next two numbers here, if you wanted to very, very strict. So you subtract the next number by the previous number. 6 minus 3 is 3. 9 minus 6 is 3. 12 minus 9 is 3. And 15 minus 12 is 3. So we can see the pattern. So the next number must be added 3 with it, the same as the next number. So here, what we're going to do is 3 minus 1, deduct it. What we have is 2. 6 minus 3 is 3. 10 minus 6 is 4. 15 minus 10 is 5. And what will be the next? So we can see the pattern. 2, 3, 4, 5. We'll need 6 here. We'll need 7 here. Hence, the next two numbers in this sequence, okay, is going to be 15 plus 6. That's going to give us 21. And after that, 21, it's going to give us 28 then. So that's the answer. Those are the answers by in our next in this next two numbers. In this next second number. For the third one, we have 1, 4, 9, 16, 25. So you may want to pause that and then try it on your own. Okay, let's do that. So we have 1, 4, 9, 16, 25. So there are two things to see in this two ways to see the answer here. So we can have 3 minus 1 is, rather 4 minus 1 is 3, 9 minus 4 is 5, 16 minus 9 is 7, 25 minus 6 is 9. So we can see the pattern that these are 3, 5, 7, 9. These are odd numbers, or numbers starting with 3 and then you add 2 all the next step. So this becomes 11, and this should become 13 then, right? So we have we need to add 11 with that 25. So that gives us 36. And next is we need to add 13 to that 36. That gives us 49. So that's how you can see this number 3. The other way which you can see this is that all of these first 5 numbers are perfect squares. So this is 1 squared, this is 2 squared, this is 3 squared, 4 squared, 5 squared, and then it's easy to see that this is 6 squared and this is 7 squared. So that's our answer. That's what our answer is here. Next is counterexamples. So as we have discussed in inductive reasoning, a conjecture may or may not be correct. So for one to make sure of its validity, I mean the conjecture's validity, you may produce a proof for it, or it is suggested that you look for a counterexample or some certain counterexample that will say that it's not true for everyone. So for instance, if we're going to consider this example. So we can observe that 11 times 1 times 101 is 1111, 4 ones. 11 times 2 times 101 is 2222, 4 twos. 11 times 3 times 101 is 3333, and so on along the process. So you may conjecture that the product of 11 and the multiple of 101 is a number where all digits are equal or the same. Thus, 11 times 6 times 101 is equal to 666. And that happens to be true, though. Try to use that in your calculators. That's going to happen. However, the conjecture may not hold true with the multiples of 101 greater than 9. We observe that 11 times 7 times 101 is going to give us 7777. There are 4 sevens here. And then likewise with 8, there it will give us 4 eights. You may try to check that if you want. Here it will give us 4 nines. But beyond the 9, will this give us um funny like 10 10 10 10 or something? So we can see that 11 times 10 times 101 and 11 times 11 times 101 are counterexamples. That nullifies the conjecture that the product of 11 and a multiple of 101 is a number where all digits are equal. Actually, if we really want to solve that and know the number or the answer of 11 times 10 times 101, the answer to that is, get my calculator to make it correct. The answer is 1111, and then there's a 0 at the end. 1111 and 0. So pretty much all the numbers are not the same. So for 11, even got worse. That's 1 2 2 2 1 1 2 2 2 1. So the conjecture is not does not hold for integers greater than 9. So the conjecture, these are examples of these are examples of counterexamples actually. Likewise here, if you have taken an aptitude test, you may have encountered the following. These are still making use of inductive or deductive reasoning, right? So for a certain example here, you may want to know what is the next number here, and then what is the next number here. Okay. Um, for instance, we're going to observe this answer here. You may want to observe the triangle. The triangle is here on the first part. In the next line, it became a blank. No, I mean, it's not shaded. Next line it comes here. It's again shaded. Next time it comes here, it's unshaded. And then I think we can see a pattern here that it revolves clockwise or counterclockwise, by the way. Counterclockwise. Okay, and one more, and then we can see that the symbols are alternating from shaded to non-shaded. So starting here, shaded, unshaded, shaded again, unshaded. So we can say that the next triangle is going to be here, and it should be shaded. Okay, and there's only one choice that gives us that. It's this letter C. And you may want to check all the others. For instance, if we're going to observe the circle is unshaded here. It still follows the counterclockwise movement, shaded, unshaded, shaded, and the circle should be here, which is unshaded, which is also the same with letter C, jibes with letter C, and therefore letter C is our answer. I'll leave this one as your assignment. More examples. This you can see a lot of times in Facebook. Let's try to answer this puzzle tree. Actually, they're the same. They're of the same value or the same pictures. Okay, let's try to answer this. So we have 3 Christmas trees are 21, telling us that this one Christmas tree is equal to 7. And then since we know that this is 7, um, 2 wheels here plus a Christmas tree, which is 7, is equal to 19. So we need to deduct 7 from that 19. That's going to give us 12. And therefore this wheels here are 6. So we know this is 6. We know this is 7. And we have the sum is 15. We don't know the value of the star. So 15 minus 7 minus 6. Well, 7 minus 6 is going to give us, what, 13. 15 minus 13 is 2. Therefore, it is equal to 2. Now, this is the real challenge. First, we can see that there are 2 stars here, obviously. This is 2 plus 2. Next is, we can see the wheel here, but there's something wrong with the wheel. It has 1, 2, 3, 4, 5, 6 like rims here, which denote 6. But here, it only has 5. Therefore, we're going to put 5 there instead of 6. And notice this Christmas tree doesn't have any star on it. Okay? So we minus 2 from that 7. That's going to give us 5. But notice the number of lines here is 1, 2, 3, 4, 5, 6. Compared to the usual 1, 2, 3, 4, 5. Now, if the Christmas tree is valued 5, okay, without the star, it means that each layer here is equal to 1. So since we have 6 layers here, this becomes 6. And notice this is now a multiplication sign. So we multiply first. So 2 plus 2 is 4. 4 times 5 is 20. 20 plus 6 is going to give us 26. So hence the answer. Okay, so that's our answer, 26. The same here. Okay, only a different photo. So we say that although these puzzles are fun, they are helping you out to keep your mind sharp in problem solving. So what's our conclusion for this video? As you may have thought of, both inductive and deductive reasoning is useful not just in math, but as well as in other disciplines or facets in life. So we find this, actually we use this in everyday life, only that we do not um really label it to be inductive or deductive reasoning. It just comes out of our subconscious, and we use that all the time. And that's the end of this video about problem solving using inductive and deductive reasoning. Hopefully you learned something from that, and hope that you like and subscribe. So thank you very much for watching. See ya.